Let G be a group and show that if AB squared equals A squared times B squared for all A and B in G, then G is abelian. So before you attempt a proof, we should figure out what the proof is saying. So it says, let G be a group. Okay, so what is a group? Well, a group is a set of elements together with a binary operation that is closed, meaning that you take any two elements in the group and you perform the binary operation on them. You get something else back that's in the group. It's associative, meaning that when you perform the binary operation, you can move the parentheses around. There's an identity element, meaning that, let's write it out here, identity element, usually you denote it with E, meaning that if you have an element of the group, say A, and you multiply it by the identity, doesn't matter which way you multiply it, you get back the same thing. And when I say multiply, I mean perform the binary operation. I'm going to refer to it as multiply, but it could be any binary operation. And then last we have inverses, meaning that every element has an inverse. And for an element A, we usually denote that by A with a little -1. And that means that you take A and you multiply it by its inverse, and it doesn't matter what order you do it in, you should end up getting back the identity element. Okay, so that's basically what a group is. Now it also says that G is abelian. Okay, so what does that mean? So if something is abelian, that means that for any two elements A and B in the group, A times B equals B times A. You may also have heard of this as being the commutative property. So that's what we're trying to show. We're trying to show that AB equals BA. So let's try and figure out how we might do this before we actually do a formal proof. So we have AB squared equals A squared times B squared. Okay, well, what does it mean to square something? That's AB times AB. And A squared and B squared. Okay, that's like A times A and B times B. Well, then I can cancel an A on the left and a B on the right, and then I'll have BA equals AB, and that's what I want. So I think we're ready to attempt a proof. So to begin with this proof, we should probably start by saying let G be a group with A and B being elements of G such that AB squared equals A squared B squared. It's good to just restate what we know. So also be sure to use complete sentences for a proof. Next, we can say that AB squared equals AB times AB, and that's the same thing as AB, AB. Okay, then we can say that A squared B squared equals AABB. Okay, this is all stuff that we did before. So now we know that since AB squared equals A squared B squared, we can say that ABAB equals AABB. Now we're going to use the cancellation laws that we talked about before. So then, multiplying on the left by A inverse, we have A inverse times A times B times A times B equals A inverse times A times A times B times B. So what we're really doing, and I didn't write it out here, is saying that A inverse times A, oops, there's my A inverse times A, is the identity element, and the identity element multiplied by anything gives you back the same thing. So this expression right here is really saying A inverse times A, that's the identity element, times B times A times B, is really just B times A times B. If you want to write it out and be a little more explicit, fine, go ahead. But I think this is fine, gets the idea across. So now we can say, multiplying on the right by B inverse, then that is going to give us, after you multiply on the right, so here's my B inverse on the right, that I'm going to have BA equals AB. Well, it's perfect. That's what I want to show it's abelian. So I can say G is abelian, and I've proved what I need to prove.